Okay, hi, I'm Daniel Zhang. Today I'm going to be talking about sorting. So these are the topics we're going to cover. We're going to cover sorting, selection sort, like algorithmic speed, and merge sort. So the first question is, why sorting, right? Sorting is really important because it's just like a fundamental computer operation. It's in everything you do. I mean, think about Excel. You know, there's the sort function in Excel. There's no sorting in Word, but there's a lot of sorting in database. It's a pretty fundamental computer operation. It's been a big question in computer science since the 50s, and it's mostly solved now. There's like dozens of different sorting algorithms, but I'm going to talk about selection sort because it's the simplest, and then I'll talk about merge sort because it's a lot faster than selection sort, and it's on the AP test, so that's also important. Okay, so let's start with selection sort. Okay. So how does selection sort work? Well, selection sort is the easiest, so it's a very simple principle. Find the maximum element and then move it to the end. And then recurse. And by recurse I mean keep taking the list without the maximum element, because that's at the end, and just keep sorting that. So here's an example. Right. So here's our list, right? And it's like 5, 2, 4, 1, 6, 3. So we find the maximum element, right? So you look through the list, here's the max. So this is the maximum element right here. And then we swap it to the end. So we swap it to the end, so the end is now sorted. So we don't worry about the end anymore. So what do? So next time, we look through the max again, and we find this is 5, right? Because we're not worried about the 6 anymore. So we swap it to the end of the list now, like not including the 6. Right? Whoops. 3, 2, 4, 1, 5, 6. So now this is the sorted part. Right. So you keep doing that, and eventually, you know, after many recursions, well, 4 more, you'd get 1, 2, 3, 4, 5, 6. Okay. So that's selection sort in the nutshell. You know, find the max element, put it to the end, recurse. And it makes a lot of sense. It's pretty simple. But you can see why selection sort is really slow, because you have to go through like the entire list. But because, you know, we're computer scientists, we need a way to quantify exactly. We know it's slow, but we want to know how slow. So that brings us to speed, right? And so it's kind of in the common sense term, you know, like velocity, how fast we're going, but that's not really what we're concerned about in computer science. What we're concerned about in computer science is how the function behaves as the input size grows large. So I'll repeat that again. How the function behaves as the input grows large. And the reason that's important is because when you think about it, let's say we only have a list of 100. The difference between like selection sort and merge sort is not very big. What we're really concerned about is what happens when we get like 1 billion items, or 2 billion items, or 10 billion items. We want to know how the function, how many operations the function takes when it grows really large. So, number of operations. Operations is really what we're looking at. Number of operations. So, we'll go back and look at our selection sort example. So we have a list of size 6. So the first time through the list we have to make 6 operations because we have to, you know, like compare each of these to each other. So the first iteration is 6. The second iteration, because we don't have to worry about this, is 5. So it's 1 minus the total. And then the third time we go through the list, because 5 and 6 are blocked, we'd have to make 4 operations. So how do we quantify that? Well, essentially we can make a table, right? So this is the iteration, and this is the number of operations. So iteration 1, we have to make 6 operations. Iteration 2, we make 5. So really what we're saying here is we have n operations, where n is the size of the list. The second time is n minus 1. The third time is n minus 2 operations, right? Because we made like 6, 5, 4. And then all the way on our nth iteration, we only make 1, right? So if we only have 1 element left, you only have to make 1 operation. So now we want to know the total number, right? So total number of operations. And so that equals to, so we'll just go up. So you have 1 operation plus 2 operations plus 3 iterations plus dot 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 all the way to n. And so all you guys have taken algebra, so you probably know that this is a very famous sum. So this is n times n minus 1, 2, and that's approximately n squared. So sorry, the board is not perfect, but there's approximately n squared operations. So that's a pretty bad sorting algorithm. That's actually, I think, about the worst you can get, unless you code really close. So we'll talk about merge sort quickly. Don't have a lot of time left. But merge sort is far better than selection sort. You get n log n operations, so it's a pretty significant difference. I mean, if n is like 10 billion, that's a huge difference in operation. So how does merge sort work? Merge sort has 3 parts. You break the list in half, effectively. In half. Sort each half. Recursively. And then you merge. And this is where the merge sort comes from. So let's take our example. So we hold up like what? 2, 5, 4, 1, 6, something like that. So what happens is you break the list in half. You break it at its midpoint. Right? So this is the break. And you get 2, 5, 4, 1, 6, 3. And then you recursively sort. So I'm not going to step through all the little steps because I don't have enough time, but effectively you just recursively sort. So you run merge sort on each of these lists. So 2, 4, 5, 1, 3, 6. And then you merge. So you put these lists together. So how do you merge? Well, you merge, you just kind of, it's pretty simple. You just start at like the 2 smallest elements, 1 and 2. Well, 1 is smaller, so you write 1. 2 and 3, well, 2 is smaller, so you write 2. 3 is smaller, 4 is smaller than 6, 5 is smaller than 6, put 6 on the end. So this is really interesting because if you think about it, this brings up 2 points. First, in terms of speed, as you can see, like in this small example, merge sort doesn't seem a lot faster than selection sort. But when you get to really big things, merge sort makes a huge difference. Why? Because it's a lot easier to sort small lists and then put things back together than it's to sort a huge list. Like if you had 10 billion terms and you had to go through all of them, like you do in selection sort, that takes forever. But if you can break it down into small lists and sort there, it's a lot faster. So thank you very much. My pleasure to teach you today.